In this video, I'm going to talk about synchronous counters. Now, up until now, we've been talking about asynchronous counters. The main difference you should notice with synchronous counters is that the external clock, here's a clock right here, goes directly into the clock of each flip-flop. Here it goes into this first clock, here it goes into the next clock, into the next clock, and into the last clock. Now, you might recall for asynchronous counters, the external clock only went into the first flip-flop, and every other flip-flop was clocked by the output of either Q or not Q. Do you remember that? Q or not Q went into the clock of the next flip-flop. Here, all of the clocks are clocked from an external clock. I know I'm saying clock a lot, but that's the way it goes. So what that causes to happen is it causes all of the flip-flops to toggle at the exact same time. There's no ripple effect, there's no delay. So this is actually a faster counter. It's a better, in many ways, a better counter than the asynchronous counter. So again, the external clock goes to each clock. Each flip-flop is toggled at the exact same time. There's no delay or ripple effect. All right, let's talk about this extra logic that's required. Now, I haven't talked about these gates yet. We're going to, in the next slide, we're going to talk about what this is used for. Why do I need these AND gates here? So before I go back to the synchronous counter and we look at what those extra gates are, let's just review counting in binary. Now, I know you know how to count in binary, but I just want to talk about exactly what's happening here. So I want you to think about when does each bit toggle if you're counting in binary. So Q0, of course, is the ones place. I can put a 1 there. Q1 is the twos place, and then Q2 is the fours place, and then Q3 is the eights place. So think about, well, Q0, of course, toggles every single time, right? I keep flipping 0, 1, 0, 1, 0, 1. When does Q1 toggle? Well, you might notice that Q1 toggles when the bit before it, when Q0 is a 1. So here Q0 is a 1, on the next count, Q1 toggles, it becomes a 1, right? It stays a 1 until Q0 is a 1 again, and then it toggles, it changes. On the next count, it changes back to a 0. So every time the bit before Q1 is a 1, on the next clock pulse, it toggles. Well, let's see when Q2 toggles, right? Here's Q2. It's all zeros initially until the two bits, until these guys are both ones. And then on the next count, Q2 toggles, right? So this bit will toggle when everybody before it is 1. So here it's 1, 1, 1, 1. On the next count, these guys before it are now both 1s. On the next count, this toggles again. It becomes a 0. So each bit toggles when all the bits before it are 1s. Let's look at Q3, for example. So Q3 is all zeros up until everybody before it is a 1. So these are all 1s. It's getting a little messy here. And then on the next count, Q3 toggles. So each bit, when you're counting in binary, each bit will toggle when all the bits before it are 1s. Then on the next count, I should say, when everybody before me is a 1, on the next count, I will toggle. So keep that in mind. Here we are again looking at the synchronous counter, which we just looked at. And you know, of course, the clock, I think I did this part already. The clock comes from the external clock, right? So each guy is clocked by the same external clock. So then we're going to talk about what these extra gates are, what these extra AND gates are. Well, what they do is they cause each flip-flop to toggle. So let's look at the ones place here. This is the ones place, right? It comes directly from the clock. This is the twos place. Notice in the ones place, J and K are always powered. So this flip-flop will toggle every time the clock pulses, right? It's in every time the clock, this is a negative edge triggered clock. So every time the clock goes down, this first flip-flop will toggle because J and K are both 1s are in toggle mode. Well, check out the next flip-flop. J and K are not powered. J and K come from, let's trace this around, they come from the previous Q. So in other words, when Q0 is a 1, when the light's on, J and K will toggle the next time the clock goes to 0. It's negative edge, right? So this is exactly what we're talking about. The twos place toggles when the flip-flop before it, when the ones place is a 1. All right, let's look at the next flip-flop. Here, J and K come from the previous, I have an AND gate here, come from the previous two, from the previous two Qs, come from this Q, and let's follow this one around, and come from this Q if I go all the way around here, right? So this is the 4's place. The 4's place will toggle when this Q is on, when this is a 1, and when this Q is on. Well, that's just what we talked about in that table. The count will toggle, the 4's place will toggle when the two previous flip-flops are both 1s. And if you look at the 8's place, this is the 8's place, you can guess what's going to happen. I have an AND gate here, and it comes from the output of all of the previous Qs. So when this Q is a 1, I can trace it around like that. I'm getting a little messy. When that guy's a 1, and when that guy's a 1, and when the guy before it is a 1, if you trace these all around, you'll see that this AND gate comes from this Q, and this Q, and this Q. So when all of the previous Qs are 1s, the 8's place will toggle. That's just what we talked about in the table. So if you're going to build a synchronous counter, two things. The clock has got to come from the same external clock here, right? It goes into every single clock. And then you have to add a little bit of logic to cause each flip-flop to toggle appropriately. And each J and K comes from the Qs of all of the previous JK flip-flops. What do you think you would do to count down? Well, give that a thought. The only thing you need to do to count down is change where these AND gates come from. That's your little hint. I think it's going to be obvious. All right, let's take a look at one last synchronous counter. Now here I'm actually counting. You can see I'm toggling the clock here. Look how nice that thing counts. There's no flickering effect as you go from one digit to the next. And let's see if we can figure out what this is going to count to before I actually complete the counting, or maybe you saw it already. So again, this is a synchronous counter. I can tell it's a synchronous counter because the clock goes directly into each of these clocks, right? You're following that. And I have these extra AND gates that cause each JK flip-flop to toggle when all of the previous Qs are on. So this first JK flip-flop comes from the previous Q, right? This is the 2's place. This JK flip-flop, the J and K come from the previous two Qs ANDed together. And the last JK flip-flop, excuse me, comes from all three previous Qs ANDed together. And I think if you trace these wires back, you'll see that the output of this AND gate comes from this Q and this Q and this Q, right? So we just talked about that in the last slide. And just like we've always done before, you can start the count based on the output of either a NAND or AND gate. Now here, the output of this NAND gate goes to all of the clears. So I bet this guy's going to start counting at 0. And the input to this is what the count limit is, what it stops counting as, what it resets on. So I can see it's coming from this Q. So that's, think of that as a 1, this not Q, this Q, and this not Q. So when I get to 1, 0, 1, 0, or that's binary, or a 10 in base 10, it should reset. So the count range of this should be 0 to 9, and it resets on 10, and I think that'll work, but let's just check it out. Yes, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and on 10 it resets, just like every other counter you've worked with. All right, get to work on the lab.